Hey guys, so this is the lecture for Trig 1.1 all over angles. Chapter 1 is where we're really going to get the foundation for all of trigonometry. We're going to talk, hopefully a lot of it is semi-review for you from a geometry class maybe that you've had, or even some algebra classes that you've had in the past. But chapter 1 is all over angles. And what I've done is I have made all of my lecture notes available to you on the Course Compass site. So my Math Lab, Pearson, whatever you want to call it. It's there under the notes drop down box. You can download them, you can print them off, you can reference them. But for my videos, I will have them screen shared with you as well. And then I will have the video up so that when it comes time to needing to do some work on the board, you can watch that live instead of just having my notes or just having me listen to me read my notes. Now, that being said, chapter 1, section 1, all over angles, it does start with quite a bit of terminology. There's a lot of definitions. There's a lot of different specifications that we have to kind of have at the beginning before we can really dive in and do some math with this stuff. So I guess I'm kind of giving you that as a heads up because 1.1 is a little bit longer in terms of my lecture notes. Usually my lecture notes are only like a front and a back. This one's definitely front and back of 2 pages and the front of another page, but the first whole front and back page is really more reference and definitions. But we're going to go through it and I'm going to talk through it a little bit. So if you don't want to listen to me read pretty much all of the front, you can read and then skip ahead if you so choose. But let's look at these notes. First, we have lines. Line AB. Sometimes you'll see that written as the capital letters AB with a line drawn over the top. Lines do have arrows on their ends, signifying that they go on forever in either direction. If you don't have those arrows, you're not actually a line. You're a line segment. So it is important to have those lines both in your reference and in your drawings of lines. So a line is made up of 2 distinct points. This time it's A and B, and it, like I said, it continues on for forever or for infinity in either direction. And so there is this AB with the line over the top is how we would write the line AB, like shorthand. And then this longer picture where I have a line with 2 points A and B on it, that's how we would draw the line to represent that information. A line segment, like I said, though, is one where you don't have those arrows. It's not going to go on for forever. It's a portion of a line that begins with A and ends with B. So it's part of a line and it stops, it has the end points A and B. So when we shorthand that, it's just AB with a line over the top with no arrows. And when we draw it, again, we don't have those arrows because it doesn't go on for infinity. It stops at those 2 endpoints. A ray is kind of like half line segment. A ray from A to B means that you have an endpoint at A, and then it's going to go on for forever in the B direction. Rays are important in terms of like which way you write it. If I write like I have there, well, that one doesn't work. If I write ray AB like this, then what I'm telling you is I'm telling you I have a ray that starts at A and it goes on for infinity, but it also goes through B like this. If I write ray BA, then I have a different situation. Then I have one that starts at B that goes through A and goes on for forever. So the ordering of your letters when it comes to a ray is important because it does tell you which side is your end point and which side you're shooting off towards infinity. So a ray is a portion of a line which starts at A and continues through B and beyond. Or in my second example, it starts at B, continues through A and beyond. So do be careful, or at least aware of that situation that can pop up when you're talking about rays. So line, line segment, ray. The next is angle. I drew a little angle there. That's usually the symbol we use to indicate an angle. An angle is two rays in a plane with a common endpoint, and that common endpoint is called your vertex of your angle. So here's a general picture with all the different parts labeled. We have a ray that shoots up towards upward. We have a ray that shoots horizontally, and this is our angle. The angle is actually this bit that's inside, kind of like think about like a Pac-Man mouth. Your angle is what's inside. You have your initial side. Usually when we write these or draw our angles, this is kind of our standard position, which we'll talk more about here in a little bit, where we have our horizontal ray, and then we have our angle shooting up out of that ray. And the angle is the amount that's in between those two. So we have our initial side. That's kind of like our starting side. If you think about angles, they're kind of like they open up like this, and this bottom part is our initial side. And then our terminal side, that's where our angle stops. So we start at our initial side, and then our angle goes until it hits the terminal side. And then we have our vertex. So that's what our angle looks like. We can think about angles as either going counterclockwise in their rotation, which is generally what we think about. We think about things moving counterclockwise, and thus we have a positive angle, or we can sometimes talk about clockwise rotation, which means that we have a negative angle. So if you look here, I have drawn the same angle. Well, in terms of the rays that I've drawn. I've drawn the same rays, but I'm talking about two different angles. The first angle, the one on the left, the positive angle, is actually the bigger angle because I start at my initial side and then I rotate all the way around until I hit back here at my terminal side. And so it's this really big arc of an angle there. That's a positive angle. I moved counterclockwise. But over here on the right-hand side, it's the same drawing, but I've moved clockwise. So I start at my initial and then I move down clockwise until I hit my terminal side, and that's a negative angle. So we would call this, and I also labeled it with some letters so you can see how we talk about angles. This is either angle ABC, or we could talk about it as CBA. But either way, notice that that B, our vertex, is in the middle, and that's what's important. The vertex has to stay in the middle. If I'm talking about angle CAB and I'm trying to get somebody to notice this drawing, then I've actually labeled it wrong. And somebody's going to be looking for a totally different angle. And so when you label your angles, it is important that the middle or vertex is in the middle of your labeling. I would say 90% of what you will deal with is going to use this counterclockwise rotation with the positive angles. And even later on, when it comes to our negative angles, a lot of times what will happen is instead of playing with the negative angles, we're going to convert them into positive angles before we actually do any trigonometry or algebra with them, just because they're a lot easier to use than their negative counterparts. So that's how you get those. All right. So let's talk some more about different types of angles. Up here at the top, I did draw the shorthands of the pictures for line, line segment, and ray, just so that we would have those as we move forward, because they are on the front, but then I wanted to make sure that you had them on this page as well. So degrees and types of angles. There's really 4 different types of angles, like if we're talking just single angles, and then we're going to talk about a couple of, like, if you combine 2 different types of angles, we can have 2 different styles. So the degree is what we use to as our unit of measurement for an angle. So 1 degree is 1/360th of a rotation in a circle. So what happens is in trigonometry, what we're really talking about a lot is we're talking about angles, but these angles actually come from circles. And so that big angle that we were just looking at just a few minutes ago, if you noticed whenever we went like this was the angle and we had our positive rotation. Notice how my angle was almost like almost a complete circle. Do you see that? It almost made a complete circle. If I do make a complete circle with my angle, then I actually have an angle that is 360 degrees, or is a circle. A circle contains 360 degrees. And so when we talk about the measure of our angles, we're going to talk about them a lot with degrees. So there's 4 different types of these angles. There's acute angles, there's right angles, obtuse angles, and straight angles. And the different variations of these angles depends upon how big or how many degrees these angles have. So an acute angle is an angle that measures between 0 and 90 degrees. It can't equal 0 and it can't equal 90. It's got to fall in between that spectrum. And so if you look down here in my notes, this first drawing at the very bottom on the left-hand side is an acute angle. This little circle with the line through it is called theta. It's a Greek letter, theta. And usually that's what we use to indicate angle measurement. And so you're going to see that a lot. You're going to get hopefully pretty good at drawing it. And it should start just secondhand nature should start happening. But there's our acute angle. So 0 is less than theta, which is less than 90 degrees. That's kind of the limits that we have on the measurement for acute angles. The next type of angle we can have is a right angle. A right angle measures exactly 90 degrees. It can't be 91, it can't be 89, it's exactly 90 degrees. It's completely up and down. And so that is a right angle. That's the second picture where theta has to equal 90 degrees. This 90-degree aspect comes up in algebra, it comes up in college algebra and in all the other math classes that you've probably had in terms of like perpendicular lines. When we talk about those in algebra, what happens is you have this line that runs this way and you have this line that runs this way and they intersect. And what makes them perpendicular is that they intersect at 90-degree angles, meaning that they have these perfect little 90-degree sections here. That's what happens, because you can intersect like this, but those aren't 90-degree angles. And so then you're just intersecting lines. You're not perpendicular lines. So you do see 90 degrees elsewhere, not just in trigonometry. But that's what makes right angles special, is that they have to be 90 degrees. Obtuse angles have a measure between 90 and 180. So just like acute angles can't equal 0 and they can't equal 90, obtuse angles can't equal 90 and they can't equal 180. They can be anywhere in between though. So that's the third picture, where 90 degrees is less than theta, which is less than 180 degrees. And those are your obtuse angles. A lot of times the play on words here is your acute angles, they're small, so they're cute. Your obtuse angles are really big, so like obese. Like those are kind of the play on words that we kind of look for. The last kind of angle that you can have is something that's called a straight angle, which is one that measures exactly 180 degrees. So it can't be more or less, it has to be exactly 180. And when you're exactly 180 degrees, you're a flat line. And so we don't talk a ton about those, but we do use the straight line concept to introduce other types of angles. Because there's 2 other types of angles that we can kind of talk about, but when we talk about them, we're really talking about pairs of angles. If you have complementary angles, then that's when you have 2 positive angles whose sum is 90 degrees. What that means is you have an angle A and you have angle B, and when you add them together, you get 90 degrees. Those are complementary. Supplementary angles is where you have angle A and you add to it angle B and you get a straight line or a straight angle, that 180 degrees. So those are the 2 different types. Sometimes on your homework and things, you're going to be asked to find the complement or the supplement to a given angle. And that's what you're going to see here on the first example, where we finally get to do some math. and not just listen to me yammer on and on about all these different types of angles. So let's look at it. We're given the angle of 40 degrees. So 40 degrees is our starting angle. That's what they're giving us. And part A says to find the complement. So we need to find the complement to 40 degrees. Well, I know that complementary angles have to add together to give me 90 degrees. That's what I know from the definition. So that means if I have 40 degrees and I add to that the complement, I should get 90 degrees. So hopefully algebra hasn't been that long ago for you, and you can say, okay, well, I'm going to subtract 40 from both sides. So the complementary angle in this case is 50 degrees. Part B is going to be very, very similar. Only this time we are going to find the supplement. Now the supplement is what do we add to 40 degrees to get us to 180? Because we have 40 degrees plus its supplement has to equal 180. Now, some of you might be asking, okay, I'm good with algebra. Do I have to write down these equations? Or can I not just say, well, the supplement for 40 is going to be 140? Absolutely, you can. I'm not one of those teachers who says it's my way or the highway. You're going to do as much or as little as you actually need to in terms of writing down your work. If it is a lecture video situation like it is right now, odds are I'm going to always give a lot more explanation just because we're not under any type of time constraint in terms of how long my lecture video can be. When we are in class, I usually go a lot faster because I'm under a 50-minute time constraint. You guys can pause the video, fast forward the video, or do whatever you want with the video. And we can't do that in class. So just know my videos are usually longer than my actual lectures that would go along with this, but that's there so that I can actually give you more tools so you can be even more successful in this class. So that was my little sidebar. Let me come back over here. In order to find the supplement, I would subtract 40 from both sides so that the supplementary angle would be 140 degrees. So that's nice. Now, sometimes though, they're not going to give us the actual angle, and that's what we're trying to find. We're going to have to figure out what these angles are. So I'm going to draw this picture because I don't want to pull it up there. It's going to give it a, well, actually I can block it with my video. Hold on. Don't look. Okay. Oh, you can see the other problem. Hold on. There we go. I'm still going to draw it up here, but there we go. Our next example, we're going to find the measure of the given angles. Okay, so we're given kind of this general picture, and they have a lot of stuff labeled on this picture, but we don't actually know what the measures of these angles are. But here's what we do have. We have this right here. And if you notice this little box in that corner, which I didn't specify earlier, but I should have, you saw this box actually up there under the example for 90 degrees. When you have that little square box in the corner of an angle, it's telling you that that angle measures 90 degrees. It's like the special little symbol we put there. So we do know that we have a base angle that's going to equal 90 degrees. But then what we have is we have this other angle that shoots up in the middle like this. And what they tell us is that this space right here has a measure of 3x degrees. Whereas this angle up here has a measure of 6x degrees. But the problem is I don't actually know what either of those angles measure. I know that the big angle measures 90, but I don't know what this little angle measures or what this bigger angle measures. And so we have to figure that out. Well, how do we do it? Well, this little angle right here, if I add to that bigger angle up there, I know that it has to equal 90 degrees. So I have the 3x plus the 6x, and I'm going to set it equal to 90. So 3 plus 6 is 9. Divide both sides by 9, and I find that x represents 10 degrees. So if x represents 10 degrees, and this first angle is 3 times x, then that means this first angle measures 30 degrees. Similarly, that means this top angle, or the larger angle, measures 60 degrees. Because I found out what x was, and then I was able to plug that in for the given values that we do have up there on the picture that they give us. I'll try and leave that one up there too, so you can see the work. B is going to be very similar, only instead of this time, you notice we had a 90-degree angle. If you look at B, notice how B looks like a straight line, and that's because it is. So we're going to have a straight angle like this, and a straight angle measures 180 degrees. Where this part right here, according to our picture, is 6x degrees, whereas this part over here is 4x degrees. But the process that we're going to use is exactly the same as the last one. Only instead of taking 4x plus 6x and setting it equal to 90, now I have to set it equal to what a straight angle is. And hopefully you're like, well, a straight angle is 180, and you would be correct. So we have 6x plus 4x equals 180 degrees. 6 plus 4 is 10. So x equals 18 degrees. And if x equals 18 degrees, and this first angle is 6 times x, that would be 6 times 18, which is 72 degrees. Yeah, no, 108 degrees, excuse me. 108. Similarly, over here, we would have 4 times x, which is the 18. That's where we get the 72 degrees. And you can kind of check yourself in that 108 plus 72 does give us 180. If it gave us something else, then we probably did some algebra wrong, some little math error somewhere along the way. So those are some different styles of problems that you could encounter where you use the definition of complementary, which is part A, or supplementary, which is part B, to find out what these different angle measurements are. Okay, let's do some more stuff. Slide this over here. Slide this down here. So there's a couple different ways that we might indicate the measure of an angle. So notice I have the measure of angle A just written there in words, and then I have equals. And sometimes you'll see that, and I noticed our textbook used it some, where you have M, that lowercase m, which means the measure of, and then in parentheses, it actually wrote out angle A. A lot of times the way that I represent the measure of an angle is the next way, with the M, with the angle symbol, and then the A. So that's how I like to write it, this M angle A, and then I would write equals, and then I'd write like 18. That's how I like it because it's nice, it's short, it's condensed, and usually it keeps things pretty organized, and that's how I like to write it. Some books even go so far as to just write it as the capital letter. I don't love that, but sometimes they do. So I like to mention that those are all different ways of writing the exact same thing. And you could see it in any one of those methods as you approach your homework, quizzes, and your tests. Okay, so we talked about how we use degrees to measure angles. But you can measure angles also with minutes and seconds. And this really comes into play a lot if you do any type of traveling, or if you look at a map or a globe and you start thinking about longitudes and latitudes, and they tell you, you know, so many degrees north by so many degrees west and all this kind of stuff. This is actually where a lot of it comes in from. And it's because our world is a sphere made up a whole bunch of circles. And so we use this kind of trigonometry and math in order to talk about locations and distances and things like that. So we are going to have to talk about minutes, and we are going to have to talk about seconds. And now I'm not talking about minutes and seconds in terms of time. I'm talking about minutes and seconds in terms of measurement. And that can be a little bit confusing because the words are the same. And I think the reason the words are the same is because they do kind of work the same. We are talking about, you know, when 1 minute, if you look at it up here, 1 minute equals 1 with this little hash mark. That's how we write that, which is 1/60th of a degree. And so think about minutes in terms of time. 1 minute is 1/60th of an hour. And so when we talk about minutes in terms of angles, it's very similar. It's still 1/60th. It's just instead of an hour, we're talking about a degree. And so 1 minute is 1/60th of a degree. If we took 1 degree and we took it into 60 little slices, then 1 minute is one of those. And so it follows suit then that a second, notice we put 2 little hash marks up there instead of 1, is 1/60th of a minute, just like with time. There's 60 seconds in a minute, 60 minutes in an hour. Now there's 60 seconds in a minute, 60 minutes in a degree is what we're saying. And so 1 second is 1/60th of a minute, which is 1/3600th of a degree. There's 60 seconds in a minute, there's 60 minutes in a degree. So there's 3,600 seconds in 1 degree. So you're like, oh gosh, that's a lot of stuff. It is, but what we're going to do is we're going to use different types of conversion factors in order to go back and forth between minutes and seconds and degrees. We're also going to just do what I like to dub old school addition and math, like algebra, and add some degrees and minutes together. And so I call it old school because we're going to use a vertical addition method that is very similar to the way you learned how to do addition, like way back in grade school, where we carried and we had to do that kind of stuff. We're going to do a very similar process here when it comes to minutes and degrees and things. So if you look at A right there, it says we're going to take 51 degrees, 29 minutes. We're going to add to that 32 degrees and 46 minutes. So I'm going to write them vertically like this, so I can do some vertical addition and get this all together. Okay, if you remember anything about old school vertical addition, we have to start at the far right and work our way over. So I have 9 plus 6, which is 15. So write the 5 down here, and I put the 1 up top. That's the carrying system that we're going to do. And then I have 1 plus 2, which is 3, plus 4, which is 7. So I have 75 minutes. And then I go to my degrees, where I have 1 plus 2 is 3, and then 5 plus 3 is 8. So I have 83 degrees and 75 minutes. Now, here's the thing. If we think about this in terms of time, let's just pretend it's time for a minute. If I tell you there's 83 hours and 75 minutes, like, hopefully you're like, well, that sounds a little bit weird. And it should sound a little bit weird. Because typically, if we go to 60 minutes, do we keep saying 62 minutes, 63 minutes, or do we say it's an hour and 2 minutes, an hour and 3 minutes? Because that's usually what we do, right? So the 75 minutes actually needs to be changed, okay? The 75 minutes right here is saying we have 60 minutes plus 15 minutes. Yeah. which is 1 degree in 15 minutes, because there's 60 minutes in a degree, right? So instead of 83 degrees, 75 minutes, what we actually have is 83 degrees plus 1 degree, 15 minutes, which is 84 degrees in 15 minutes. Ooh, almost ran out of the screen for you there. So if I take 51 degrees, 29 minutes, plus 32 degrees, 46 minutes, in the end, I'm going to get 84 degrees and 15 minutes. If we are talking about minutes and seconds, all of our minutes and seconds should be less than 60. If you get to a point where you have 75 minutes or 75 seconds, then that tells you you need to convert those in, because you actually have enough to have another degree or have another minute. You know what I mean? Like, I'm not going to say it took me 200 minutes to run the race. I'm going to tell you it took me, 2 hours or 20 minutes to run the race, because that makes more sense. All right, let's look at the second one at B. I'm going to erase this. If you pull up my notes, or I can scroll up here in a minute. Actually, I can scroll up right here. I'll just move my video. Block the answer. Then you can see that I have the problem worked out right there for you. All right, let me erase. So that was adding degrees with minutes. Now we're going to do some subtracting. B says we have 90 degrees, take away 70 degrees, 12 minutes. So I have 90 degrees minus 73 degrees, 12 minutes. And you're like, okay, well, that doesn't really help me, because here's what's wrong. If I'm doing subtraction, I have to actually have something to subtract it from, but I don't have any minutes over here. I just have degrees. I don't have any minutes to subtract from. So what I'm going to do is I'm going to convert one of my degrees into 60 minutes so I can do my subtraction. So instead of having 90 degrees, I'm now going to have 89 degrees in 60 minutes. Yes, that looks weird, but this isn't our final answer. This is just a tool that we're using to get through the subtraction. Because what this is going to allow us to do is actually do the subtraction. Like this. I converted one of my degrees into minutes so that I can do my subtraction. And again, we're going to do old school vertical subtraction. So right here, we start at the far right. I have 0, take away 2. I can't do that. I can't have 0 and then take 2 from it. It doesn't work. So I have to borrow. I have to borrow from this 6, because you go over one place. So instead of having a 6 there, I'm going to have a 5. And then I borrowed 1 from there. So that means I'm going to have 10 over here. Hopefully this isn't totally new math. It's just old math. So you might have to dust it off a little bit. But now I can actually do my subtraction. I have 10 take away 2, which is 8. 5 take away 1, which is 4. So I have 48 minutes. Then I move to my degrees. I have 9 take away 3, which is 6. 8 take away 7, which is 1. So I have 16 degrees and 48 minutes. And that's how we're going to do some of our calculations when it talks about degrees and minutes and seconds. None of these had seconds in it, but if it did, we would just have another column that would have our seconds in it, and we do the same kind of stuff. All right, let's look at the next stuff where we're going to start converting our degrees, minutes, and seconds into decimals, into the decimal representations. So decimal degrees. If I have 12.4238, like I do right there, that's really saying that what I have is I have 12 and then 4238 over 10 thousandths of a degree. I don't know how long ago it's been since you've dealt with decimals at all, but let me give you a general little overview thing here, where if we have a decimal, and then we have our numbers out here, and we have our numbers out here. This first place is called our ones place, like to the left. That's our ones place, and we have our tens place, and we have our hundreds place, and we have our thousands place, and so on and so forth. And that's as we move to the left. Those are like our whole numbers. But when we move to the right, we're talking about fractional pieces of numbers. They're not whole numbers anymore. And over here, we start with our tenths. So it doesn't go once. We don't have a once spot. We just have tenths spot. And then we have our hundredths spot. And we have our thousandths spot. And then we have our 10,000ths spot. And so on and so forth. So in this case, we were talking about a decimal that went out 4 units, went out 4 places. If you go out 4 places, you're in the 10,000th spot. And so that's why we stuck that decimal, that 4238, and we stuck it over 10,000. If it had only gone out 2 places, then we would have only stuck it over 100, and we would have done it that way. And so that's how we do that to convert it back and forth. Let's see this actually played out on the next problem, where we're going to convert 74 degrees, 8 minutes, and 14 seconds into a decimal degree. Now, notice that when we talk about minutes and seconds, even if it's only a single unit, we typically write it as a double unit. What I mean by that is that we didn't just write 8 minutes, we wrote 08 minutes. And that way it's very specific that we didn't accidentally leave a number off anywhere. So what do we do? How do we get a decimal representation from that information? Well, we have 74, sorry, I want to write it up here, 74 degrees, and we have 8 minutes, and we have 14 seconds. In order to write this all as a decimal in terms of degrees, then we have to write minutes and seconds in terms of degrees, in terms of degrees. So we have 74 degrees, that's already written as a degree, plus, and then here's what you have to think. How many minutes are in a degree? Well, we have 60 minutes in a degree. So we're going to have 08 over 60, or 8 over 60, however you want to think about it. We have 8 minutes over 60 minutes, and that gives us a degree. Plus, we have 14. Now here it gets a little bit trickier because we don't have 60 seconds in a degree. How many seconds did I say we had in a degree? We have 3,600 in a degree. So what we are in essence doing is we are converting our minutes into degrees, and we're converting our seconds into degrees so that we can have just one single decimal degree representation. Because while this is really nice for traveling or for map reading and things like that, when it comes to algebra or trigonometry, a lot of times this isn't going to be very helpful. So we need to get this in a decimal to actually be able to use it or do computations or measurements and things like that. So you are going to want a decent scientific calculator for this class. There's a lot out there, but I recommend Texas Instruments. Usually they're the most user-friendly ones, but if you like Casio, or if there's another brand that you like more, you can go with that and do it your own way. But at this point, I would type this whole thing in my calculator. And even though you don't know it, your homework's going to tell you how many places to round it to. This one says round to the nearest thousandths. So all of this is approximately, squiggly equal signs means approximately 74.137 degrees. So this 8 divided by 60 plus 14 divided by 3,600 is approximately 1.37. So not super big, but that's how we'd write 74 degrees, 8 minutes, and 14 seconds as a decimal degree, is by using that conversion factor to get it over there. We're going to do another one. Only this time, we're going to go the opposite direction. We're going to go from the decimal, and we're going to go back up to the degree, minutes, and seconds. Because if we go one direction, it's nice to be able to know that we can go the other. All right. Let me try and cover up the answers. This, every time I move my video, it covers different things. This time we're going to convert 34.817 degrees to degrees, minutes, and seconds. So we have 34.817 degrees. And we need that to be converted into degrees, minutes, and seconds. Well, the nice thing is you already know the degree part, because the degree part is the whole number aspect. It's the 0.817 that we don't know how many minutes and how many seconds we have. So we have 34 degrees plus 0.817 degrees is what we have here. And we need to convert this over. So we got to get some minutes out of it. So this is where we're going to do a conversion factor. I talk about conversion factors in my Math 20 class. If you take a chemistry class or a biology class, especially a chemistry class though, I know that they talk a ton about doing different conversion factors. And so a conversion factor is where you go from like minutes to hours, and it's how we get there in terms of time. I was talking about time there. And so here we're going to go from degrees and we're going to convert it over to minutes. So we're not going to do anything with this 34. It's just going to kind of tag along with us until we get to the bottom. But what we're going to do is we're going to convert this 0.817. And right now it's in degrees. And we don't want it to be in degrees. We want it to be in minutes. So then I have to say, okay, if I'm going to convert it, I need to put a degree on bottom. So I have 1 degree on bottom. How many minutes are in a degree? Well, there's 60 minutes. So I put 60 minutes on top. Because here's what's going to happen. If I multiply those, then I would have a degree on top and a degree on bottom, which means my degrees go away, leaving me with just minutes. And here, even though you don't have it, it does say round to the nearest second as we're going through it. Again, your homework and your quizzes and things like that on the My Math Lab site, it has a blue box where it tells you like how many decimal places and things like that to round to. So we're going to take 0.817 times 60. So we have this 34 degrees plus, and when we multiply that, we get 49.02 minutes. All right, so we're closer. We started with only degrees. Now we have degrees and minutes. But here's what's going to happen. Notice that when we went from degrees, the first thing that happened was we took our whole part and then we put plus and then the not whole part, the decimal part. And then we converted that decimal degree into minutes. Now we're going to do the same thing with our minutes. We're going to take that decimal minutes and we're going to convert it into seconds. So we have 34 degrees plus 49 minutes plus 0.02 seconds. Or that's still minutes. We got to convert it into seconds here in a minute. Ugh, I say minute too often. So we have 0.02 minutes. And just like we did here, by converting our degree into minutes, we needed to convert our minutes into seconds. So how many seconds are in a minute? Well, there's 60. And just like here, see, I had a degree on top, so I put a degree on bottom. Here I have a minute on top, so I'm going to put a minute on bottom. And how many seconds are in a minute? There's 60. So we multiply that, and we get 34 degrees plus 49 minutes plus 1.2 seconds. This is where it's important to note that it says right there at the top, it wants us to convert to degrees, minutes, and seconds. We still have this 0.2, so we're going to round that a little bit. We're going to just round it down to the nearest second, so that this becomes 34 degrees, 49 minutes, and 1 second. Or 0, 1, I guess, sorry. We usually write it with a 0 in there. And you can see that, let me move this over, because maybe you can see it better on my notes. So we had to do these different conversion factors to convert the decimal aspect of our various quantities. So we converted the decimal degree into minutes, and then we converted the decimal minutes into seconds. And then we were done because they wanted us to get all the way down to seconds. And that's how you do that kind of problem in your homework and things as we move forward. All right. I know this is a longer one. We actually are almost done. We're going to do a couple of more terminology things and some very minimal problems. And we have 2 application problems at the very end. And we're done. So we are almost done with this lesson. And like I said, my video lessons are typically longer than my in-class ones. Just because I can go a little bit more in depth with the material, or I can write out more steps as needed. Standard position. I kind of mentioned standard position earlier when we started talking about our angles, but it is good to note what the standard position is for an angle as we reference it and start doing a lot of our trigonometry with it moving forward in the class. So standard position, you can see it there in my picture. It is labeled green, this angle, and I did put it on a Cartesian coordinate system because we are going to talk about it in terms of like the unit circle here in a couple of sections and things like that. But when we talk about an angle, like I said, your initial side is going to be your flat bottom side. It's usually lined up right there with that x-axis on the Cartesian coordinate system. And then your terminal side is the one that's up, depending on how big your angle is. If you are an acute angle, and since we are in the Cartesian coordinate system, then you're going to lie in quadrant 1, because quadrant 1 of our Cartesian coordinate system goes from 0 to 90 degrees. So that's the nice thing. When we line up our standard position with our Cartesian coordinate system, all acute angles, if we're talking positive angles, are going to lie in quadrant 1. And then a right angle, obviously, it lies right there on the x-axis and the y-axis. And then after that, if you are an angle and you're in quadrant 2, then you know that you are an obtuse angle. And then if you lie on just the x-axis, you are a straight angle. If you lie in quadrant 3, then that means you have a measure between 180 and 270. And then if you lie in quadrant 4, you have a measure between 270 and 360. And so those are the nice things about having that starting point always being the same, so that I'm not saying, well, I have a right angle, but I'm starting here and going this way. Instead, it's like, no, we all adopt this one same direction so that we can talk about angles more commonly. There are also things called coterminal angles. Those are angles that differ by 360 degrees. That means they make full rotations around. So what happens is we have an angle, but I'm telling you that we went around the circle a couple of times to get there. And so if I tell you that we have 60 degrees, I may want to know, what is a coterminal angle of 60 degrees? There's actually infinitely many coterminal angles that line up with our 60-degree angle. The first one being, though, would be 420. Because what happens is if I get to 60 degrees, I stop and I'm done. Or I can go a whole circle to hit back up there at 60 degrees. And then I've actually gone 360 plus the 60, which is 420. Or I could go again and I could add 360 more degrees to give me 780. Or I could go again and again and again. And all of those are coterminal angles. That means that while they have different degree values, because we've gone around and around the circle, I still am ending at like the same spot in reference terms of the original angle. So those are coterminal angles. We're going to do some little math or algebra with coterminal angles. You can kind of see one right there. So let's scroll down just a tiny bit. Let me write them up here. We're going to find the angle of least positive measure that is coterminal with a big number. So the least positive measure means that we're finding a value that lies between 0 and 360, meaning that we didn't loop. We didn't loop back around and hit the angle again. We want to get something that's between 0 and 360 degrees. So here's our first angle. We have 908 degrees, and we need to get to something that's between 0 and 360. So how do we do that? Well, here's how you work through these. If you have a starting degree that is positive, then we're going to subtract 360 until we get to something that's between 0 and 360. So I'm going to take this and minus 360 degrees, and that gives me 548 degrees. That's still larger than 360 degrees. So I'm going to subtract another 360 degrees. And when I do that, I get 188 degrees. So that's where I'm going to stop. Because if I were to subtract another 360 degrees, then I'd end up with a negative value. So, and here's kind of a good example because you end up with a couple of coterminal angles. 908 is a coterminal angle with 548, which is a coterminal angle with 188. And we can keep going in either direction and come up with infinitely many more coterminal angles. But this 188 degrees is the angle of least positive measure, because I can't get a smaller positive coterminal angle for this problem. Because like I said, if I subtract 360 again, then I'm going to get into the negatives. So let's look at B. What if we start with a negative degree? That's negative 75 degrees. Well, if we have a negative value, remember what that means is we went down, we went backwards. We went clockwise instead of counterclockwise. But to find coterminal angles for it that are in the positive range, we need to add 360 degrees. So if I take negative 75 degrees and I add 360 degrees, I get 285 degrees. And I actually get to stop right there because that is the smallest value that is positive, that is coterminal with negative 75. Because if I add another 360, I get a much larger number. And so that's not going to be smaller than this. So I only had to do that process once for B. For C, I have negative 800 degrees. Again, it starts negative, so I'm going to add 360 degrees to it. And that's going to give me negative 440. That's still not positive, so I'm going to add another 360. When I add another 360, I get negative 80. Well, that's not positive yet, so I'm going to have to add, I'm going to come down here, negative 80 degrees plus 360 degrees equals 280 degrees. So if they give you a positive number, you're going to subtract until you get the smallest you can get that is still positive. If you give you a negative number, you're going to add 360 until you get to the first positive number that you get to. And that's how we find the coterminal angles, and we use them to find the least positive angle. All right, last two problems here. We have some application problems. So application problems, you ever hear that word in a math class? You need to think word problems. We will deal with word problems in trig. So I will always try to write down the whole word problem in my notes, just so that you have them there in front of you, or I will reference the textbook and you can go open up the specific word problem in the textbook. If you didn't know, you do get a digital textbook that comes along with the My Math Lab program. And in your class, if you go over there, there's like an e-text button, and then you can pull up the pictures, and it looks just like you've opened a math book and it's there in front of you. And so sometimes I may not want to write down all the words in a problem, and I may put, it's page 102, number 7, and then you can open up the textbook to have the actual wording there in front of you. But these ones were relatively small, so I wrote them down. And it says a tire is rotating 600 times per minute. Through how many degrees does a point on the edge of a tire move in half of a second? Okay, so we're thinking about a tire. Here's our tire. I don't know, tire. Tire is a circle, basically, and it's rotating, and it's going really fast. It's going 600 rotations, right? 600 rotations in a minute, per minute. That's what's happening. And what we're saying is there's one little spot right here on the edge of the tire, and we want to know how far is that little spot traveling in half a second. So what we need to do is we need to do this conversion factors. This is where I'm going to show you how to do conversion factors, kind of like you would do in a chemistry class, that will help us get there. Because right now what we have is we have rotations per minute, but we kind of need to get to rotations per second so that we can figure out how far it's going in half a second. So right now we have 600 rotations in 1 minute. Okay, but I need to get over to some seconds. So I'm going to have to do a conversion factor. And the way conversion factors work is you have this big parenthesis here, and it's a lot like what we were just doing with our minutes and seconds, where I'm like, okay, I don't want minutes. That's not what I want. I want to get to seconds. So seconds is my goal. I want to have seconds down here. But in order to get rid of minutes, I have to have minutes up here. Okay, and you're like, well, okay, that's a bunch of words, but where's the numbers? Well, how many minutes or how many seconds are in a minute? I guess is better how to say it, because seconds are smaller. So how many seconds are in a minute? If we have 1 minute, we're going to have 60 seconds. So if I were to multiply straight across here, notice my minutes would go away, leaving me with a new fraction where I have rotations per second. And that's more closely where I need to get to. I need to get to rotations per half second. So if I take 600 times 1 and divide that by 60, then I'm getting that I did 10 rotations in 1 second. Okay, so if I did 10 rotations in 1 second, then I need to know how many rotations I did in half a second. So I have 10 rotations in 1 second, but I need to know how many rotations I did in half a second. We can stick that all over 1 because I want my seconds to go away because I'm trying to figure out rotations. Through how many degrees does a point on the edge of this tire move in half a second? So 10 times a half means I'm going through 5 rotations in half a second. Okay? 5 rotations in half a second. Now, that doesn't tell me how many degrees I went through, does it? That just tells me how many rotations I go through. I go through 5 full rotations of that tire in half a second. But what do we know about a circle? I mean, a tire is a circle, right? And so how many degrees are there in a circle? Well, there's 360. So what I know is I know 1 rotation equals 360 degrees. And I just found out that I'm going through 5 rotations in half a second. So that means I'm taking 5 times 360, and that's going to tell me how many degrees I'm traveling every half a second. And it's 1,800 degrees. So I did a whole bunch of conversion factors to tell me how many times I'm rotating my tire in that half a second. And then from that, I know that 1 rotation is 360 degrees. So that I'm going through 1,800 degrees every half a second. That's pretty dang fast, I think. I'll move this over so you can see it worked out right there while I erase the board. So that's how you do that style of problem. And that's how you do conversion factors for like chemistry. When you have to convert from like kilograms to micrograms, you're doing a very similar process to what we just did here. All right, and we're on to our final problem of 1.1. And it's a turntable problem. I'm actually going to leave it set up just like I have right now, because number 2, you can read the whole question without seeing any of the work right now. And it says a turntable in a shop. Okay, let me pause. In case you don't know what a turntable is, you know, way back in the olden days, it's even before me, we had big discs, and some of the vinyl is actually making its way back, like mainstream. So vinyl discs, they sell them at Target still. I know Taylor Swift always comes out with like really pretty ones, but they're the big discs, like pre-CDs, and you put them on the turntable and then put the pointer on it and it play the music for you. So that's what a turntable is. And it says a turntable excuse me, in a shop makes 45 revolutions per minute. So how many revolutions does it make in a second? So this one's very similar to what we just did, only a little bit even easier, because we only have to really do 1 conversion. What it tells us straight out of the gate is that this turntable makes 45 revolutions. I'm going to shorten that to rev. 45 revolutions every single minute. But it doesn't want to know how many revolutions we make in a minute. It wants to know how many revolutions it makes in a second. So we need to convert this over into seconds. So I'm going to do a conversion where I have minutes on top and seconds on bottom. And again, I'm going to say, okay, for 1 minute, I have 60 seconds. So if I multiply that straight across, I have 45 minutes per 60 seconds. And you're like, okay, well, that doesn't tell me much. Like, it's still 40, or not minutes, sorry, revolutions. It's still 45 to 60. But we can make that into a fraction. 45 revolutions. Because what that's saying is I have 45 over 60 revolutions per second. Well, 45 over 60, that's definitely not simplified. They both have at least a 5. They actually have 15 in common. Because 45 is 3 times 15, and 60 is 4 times 15. So the 15s cancel, meaning that we have 3/4 of a revolution per second. So it makes it 3/4 of the way around that disk every single second, which is pretty fast. And that's how you use these conversion charts. There's one, rolled it up for you. But this is how you do conversion factors in order to change basically the units that we're talking about. Instead of revolutions per minute, we talked about revolutions per second. Instead of talking about just degrees, we talked about degrees, minutes, and seconds. And that is actually the end of 1.1.